said ionic compounds are usually made up of metals. So I'm going to use N to represent the metals attached to nonmetals. Okay. About 95% of ionic compounds fulfill this criteria right here. Now I have common ions here. You learn common ions so you can name ionic compounds, right? So we're told here that when it comes to the metal, there are two main types of the metals. There are the fixed metals. These are called fixed because they only have one charge. So fixed because they have one charge. They have the same charge all the time. They're also called type 1 metals. Okay, so there are two types of metals. The type 1 metals are the fixed charge metals. The other ones are called variable charge metals. And they're called variable charge because they can have more than one charge. We have to specify the charges of the variable charge. Because imagine I'm on the phone with you and I'm talking about a metal, right? Let's call it M. And I said, well, M is combining with chloride. And you're like, well, I know of 3 M's. So which M is she talking about? Then you ask me, wait, can you specify which M you're talking about? I'll be like, oh, the one that has the +2 charge. So you will understand, I mean M+2, not M+1 or M+3, okay? If there are many M's. So metals that have variable charges are called variable charge metals. They're also called type 2 metals, okay? I don't prefer using type 2 just because, I don't know, it just reminds me of, I don't know. I just prefer variable charges, fixed charges. To me, it's more informational. The name gives you information versus type 1, type 2, because you have to know what 1 is and what 2 is, right? So naming ionic compounds, once again, the two parts of the name. The first one is going to be the metal name. You will name the cation as the metal. The second part will be the anion name. For the anion, right, you will name this as, if we're dealing with binary compounds, you're going to name this as the format STEM-ide. Okay. So STEM that's the name that comes from the non-metal, then IDE because it has a negative charge. Now, through your common ion, as I mentioned right here, you have learned the names of monoatomic ions, cations, anions, polyatomic cations, anions. If you have forgotten what these are, please stop this video, go watch the other video, the one talking about naming compounds, then come back and watch this, okay? So here we give examples of metallic compounds, sorry. Metal ions, so we have the general name of it, alkali, these are group 1s, alkaline earth metals, group 2. We have some we have some D block metals, zinc, 2+, silver plus, and aluminum is a P block metal that has a fixed charge. So you want to be aware that there are many different types of metals in the periodic table. We have the S block metals. I don't know why they're not here. The S block metals have fixed charges. S block metals. You also have P block metals. Yeah, I guess the one with the fixed charge, the one where the charge is invariant, that will be the S block metal. I see what they're doing here. I'm trying to separate the one with the fixed charge versus the one with the varying charge. So the invariant, the metal with the invariant charge is the S block metal, right? And they give you the example here. All group 1 metals are invariant. Group 2 metals are invariant. Zinc, aluminum, silver. Technically, you can put cadmium here. These are all invariant, right? The second type of metals, these are the ones that have many charges. They're variant. Of course, the first one is type 1, right? That's the name I don't like. And this is type 2. It doesn't give you much information. You have to know what type 1 and type 2 are. But type 2 vary in charge. They have more than one charge. You have to specify their names. Example of this is transition metals, right? This is going to be D block. And then, of course, the bottom of the F block, bottom of the P block, acting like D block. These are the ones I like to call the heavy metals. Heavy metals, okay? These are P block metals on the bottom of the P block that act like D block metals. So they have many charges. Then you have the inner transition metals. This would be, of course, the F block. So bottom line, the ones that have the fixed charge are S block and for sure aluminum. The ones that have many charges would be D block, F block, and then bottom of P block. P block, so say P bottom, okay? So I would say funny, but ironic enough, many of your metals have variable charges, right? As far as the abundance or the quantity is concerned, you have more that have different charges than the ones that have fixed charges. Okay. If you're looking at the name, how can you know that you're dealing with an ionic compound with a fixed charge? They tend to just have two names or two parts of the name. The first name is the metal. It's given to the metal or the metal ion. So the first name is for the metal ion. The second name is for the non-metal ion, okay? The template, like the one they gave us here, will be the element name. The metal ion is named like an element. The non-metal ion is named as an ion, right? A monoatomic ion. So for this one here, the name will be STEMide if we're dealing with a binary compound, which it says so right here. If you have a binary compound, it contains only two elements. So for example, CaO, just two elements. The first one, the metal is in group 1, so you name it as calcium. Calcium is the name of the metal ion. And then the non-metal ion will be oxide. And that follows template provided here. Element STEMide. The stem here goes with the stem word or the root word for the non-metal, okay? Focusing on patterns only for a while, you can see binary ionic compound, potassium chloride, just two names, right? Element name, so element STEMide. That theme is followed throughout, as long as it's ionic A compound. Calcium oxide, the metal comes from group 2, right? This is a group 2 metal, so it has a charge of +2. Potassium is a group 1 metal, it has a charge of +1, right? Group 1 metal, group 2 metal, and aluminum from group 3 metals tend to form type 1 ionic compounds, or they tend to form ionic compounds with a fixed charge. Okay, moving on to this right here. Now we're asked to name this. So you want to crisscross to get the charge, right? So remember when you're forming this compound, you took Ca2 plus Br minus, and you crisscross this to make the compound, right? And you got CaBr2. Now, though you're looking at this, you're thinking about it this way. The best way to do that, I say reverse crisscross. Let me zoom this in. The 2 that's down here came from calcium, so take it back to calcium, right? We're pretty much bringing it back to what it was here. And then the implied 1 here goes back to bromine. So the calcium is usually, the first element written down is usually positive. Calcium will be +2 from this, right? Because it'd be calcium +2. Bromine will be negative, so you name this calcium bromide. Okay, let's go ahead and move on. I'm going to go ahead and name here. This one here is not really a group 1 metal. You see that, right? Or group 2 metal or group 3 metal. But silver is a D block metal that has a fixed charge. So you will name it as, you want to visualize it as a reverse crisscross, right? So take the 3 back to, well, take the 1 from the end back to silver. It kind of drops off because it's implied. So it'd be Ag plus. Take the 3 back to N. It will be N3 minus. This will be silver, like you named it in the common ion. And this would be nitride. Do you have to ionize it to name it? No. I'm just trying to get you guys to see the list you memorize in the nomenclature. Okay. For our next one, so we just worked on this one here. For our next one, it says write the formula. So now we're going from name to formula. Rubidium is in group 1, so that will be Rb positive. Sulfide, group 6, like that. Crisscross these, drop the charges. We have Rb sub 2, S sub 1, but the 1 disappears, so we have Rb2S. And this is the formula. Okay. We're moving on to naming type 2 ionic compounds. In naming type 2 ionic compounds, remember these ones have many, they are multi-valent, meaning that they have many charges because they have many valence electron, multi as many valent as valence electrons. So they form cations by losing 1, 2, 3, just variable amounts of the valence electrons. Okay, here for the nomenclature, you want to recognize that these behaviors are seen in transition elements, the ones in the D block with the metals in the D block. In a transition will be in the F block. And of course, heavy P block metals, right? Example, lead, tellurium, astenate or tin, right? What was the other one I see here? Antimony. There are many over here that are actually have more than one charge, okay? So we have an example here. In our example, like before, you have to do the reverse crisscross when you're naming it, but you have to specify the charge. So let me go ahead and move on right here. For example, for Cu plus, we say this is copper 1. For Cu2 plus, we say this is copper 2. The 2 comes and the 1 comes from the charges we see corresponding to the formula of the ions, right? Okay, let's move on down here. Okay, in naming this, once again, don't go by how it looks over here. It looks like you have 2 coppers, right? No, what you have there is the number of copper required to make a neutral compound. Okay, what you really have here in the name is you have Cu2O. You want to reverse crisscross first. In reversing crisscross, the 2 goes back to the oxygen. The implied 1 here goes back to the copper. So copper is going to be 1, oxygen will be 2. Remember, the one that's written first is normally positive, the one that's written second is normally negative. So we have here copper 1 in parentheses, right? Or I, and then oxide. You will incorporate the negative ion into the name of the second element by making it I. So it'd be STEMide, right? Copper 1 STEMide. So remember, when you're dealing with type 2 ionic compounds, you have 3 parts of the name. The first one will be the element name. Second part will be the Roman number. The third part will be the name of the nonmetal. Okay. I'm not over explaining this part here once again because I have a whole video where I explain that part. The purpose of this video is bridge the gap between slide 22 and slide 51. So I'm trying to make it to the end. For type 2 compounds, you can see here you have the name of the metal. That's the name of the cation. You have the Roman number. This has to be there. It's not optional. Then you have the STEMide, right? So this would be pretty much elements, name of the metal, Roman number. This would be in the parentheses. And then you have STEMide. Or in general, the name of the anion, because it could be like polyatomic. It doesn't have to always be monatomic, right? It could be polyatomic. Okay, old school, new school. I'm sure you have named, going back over the video where we're naming acids, different acids, right? Nitrate, the egg became the egg, the ice became the us. We saw ick and us, or should I say us and egg over there. But in the acids, so I want to review that quickly. In acid, us indicates less oxygen, but it's still less. That's what we have in common, right? And then ick indicated more oxygen. Is this relative? Okay. The context here, we don't even have oxygen in any of these metals here. So ick will just indicate more, and then us will indicate less. We don't care about the oxygen here. More charge, less charge. But this is somewhat subjective, right? So you can see here, all the icks indicate more charge, all the us's indicate less charges. So that was the old school way. We call it old school. We call this retro, okay? Retro. That used to be the way. Now the new way is to actually specify the charge. This is more clear because if the person you're talking to did not know what ick was or us was, then they were as lost as anybody else, right? But if you say chromium 2, there is no question the charge in that chromium is 2. Chromium 3, there's no question the charge in the chromium is 3. Iron 2, iron 3, cobalt 2, 3. There is no question about what the charge on these cations are for the multivalent ionic compound, okay? Okay, so I've already explained that part, so I'm going to go ahead and move on. So here we are. We're not talking about finding the charges as I showed you before. Okay, when you're reverse crisscrossing, how do you know you've reversed enough or you've crisscrossed enough? I mean, there's only one reverse and one crisscrossing, right? But on campus, I'm usually asked, how do you know? You want to use the charge on the anion. So you really got to know your anions. When I say know them, right? Because they will tell you if you're done. For example, in this example here, we have, oh, my bad. Let me use the example that we have. I'm not going to do any more random examples. We have CrBr3, okay? Remember the first element or the first ion is the positive one, second one is negative. If you look on the base, if there's no number there, you can put a 1. So I put a 1 here, and the 3 is already there. I don't have to put another number. Move the 3 back up, so you're reverse crossing. The 3 on the bottom right goes back to the top left. The 1 on the bottom left goes back to the top right. So we end up with Cr3 plus Br minus 1. But the 1 is implied, so we can just rub it off. We can erase it here, right? Because the 1 is implied. We don't have to write it like that. So when you're naming this would be, because it has variable charges, chromium. Oh, let me finish this part here. Chromium 3 bromide. The 3 has to be in parentheses. Okay, chromium 3 bromide. Okay, how do you know that all you need to do is crisscross and not multiply it by a factor of 2, 3, 4, 5? Because the charge on the negative ion, the anion, has to be accurate based on what you know it to be, based on what you memorize it to be. Okay, so we got chromium 3 bromide. Moving on to this next one, SnCl2. You can do it that way or you can do it the math way. Let me do it the math way in this slide for this one here. SnCl2. The math way, you have to understand that ionic compounds are made up of ions of opposite charges combining together, right, to form a neutral compound with no charge. The net, when they combine, is 0 because the amount of negative charges balances out the amount of positive charges, right? So the overall is 0. Okay, so we're told here, take the total charge of the cation, right? Add that up. Total charge of the anion, add that up, and when you add them up, they should be 0. So in the formula, we have 1 Sn plus 2 Cl2 is equal to 0. You're going to replace the charge on the anion part because anions tend to have a fixed charge all the time, so they're less complicated. So each chlorine is -1, right? What must the 1 Sn be? When you multiply this, I have Sn minus 2 equal 0, Sn equal plus 2. So now you have what you need. Sn stands for 10, so you have 10, 2. So essentially it's Sn2 plus, right? Combined with Cl minus. Cl minus is the symbol for chloride. So you're going to name the Sn2 plus, that will be 10, 2. And then this one here will be chloride. Okay, 10, 2 chloride. Okay. We got this one here. How about we try this? PbS2. How about that? PbS2. That one's a different one from this. I mean, over here we have lead 4 chloride. I mean, yeah. For this one here, you can see how you reverse crisscross PbCl4. So the 4 comes back here. So now you have lead 4 plus Cl minus because the 1 comes back here, becomes minus. So lead 4 chloride. Let's do PbS2, right? So almost Pb, but it's not PbS, it's PbS2. For this one here, okay? Let's use the mass method. So it'd be Pb, we have 1 Pb added into 2 S's to give us a net charge of 0, okay? Each sulfide is always a -2 charge. So we have 2 -2s equals 0. Pb plus Pb minus 4 equals 0. Pb equal plus 4. So how would you name it? Though there is no number 4 here, you will write it as lead IV for 4. So it's going to be Pb plus 4 S2 minus. So when I'll talk about the reverse crisscross to get the charges, right? So this is going to be lead 4 sulfide. Okay. So you can work it out that way to get the name. The other way you can work it out is by reverse crisscrossing. So let me work on that part here as I unfold the mysteries of nomenclature. Okay, so PBS2, for this one here, you want to reverse crisscross. Put the one down here, reverse it. So we have PB2 plus S minus 1. Okay, there is no such thing as S minus 1. The S that we have, the sulfide is in group 6, is minus 2. So multiply all the top numbers by 2 to make the S minus 2. So times 2, this becomes 2, this becomes 4, and ta-da! You now have the right ions. Okay, you have lead 4, IV, and then sulfide. Do not forget that. I don't like the reverse crisscross method. I don't mind it now because I've kind of learned this stuff already. But when I was learning, I didn't like it because it was too much remembering. And then there was all these caveats, right? Don't forget this, don't forget that. There's a lot to remember. Okay, let's go ahead and continue from here. Once again, I do have a goal. I don't want to make this video too long. So let's work on FES. FES, I will do, let's see, what comes next? Oh, okay. I will do the reverse crisscross on this one here. We have a 1 here and we have a 1 here, right? Implied. So we know the first one is positive, second one is negative. So if we reverse this here and reverse this here, we end up with Fe plus 1, Fe minus 1. In chemistry, the ones are implied. You don't have to put them on there, so they're known to be there, but they're not. It's like if you know, you know, you don't have to write it down because you know. Wait, why did I write this twice, y'all? I'm trying to keep my mind focused on where I am right now because, you know, I'm like, I got all these things to do. Okay, anyway, right there. Okay, we don't have a sulfide that's -1. It's -2. So multiply all the numbers in the top by 2 to make sure the sulfide is right. So we have the right combining ratio. So we're saying here for every 1 iron, we need 1 sulfide ion, okay? Oh, all this was to say we have iron 2 in parentheses, sulfide, okay? That's the name of this. The next one is write the formula for, this one should be straightforward, right? Ruthenium is Ru. It's +4, right? +4 because the Roman numbers is given to you right here. That indicates the charge of the metal to the left or the element to the left. Oxide is O2 minus, indicated by the name that it's negative, and then it's going to have a charge of -2. Crisscross this, and we get Ru2O4. Simplify because remember that ionic compounds are written as empirical formula format. So they have to be simplified. So it'd be RuO2, ruthenium 4 oxide. I know we're saying 4 and there is no 4 here. Where is 4? Oh my goodness. I just remembered. My nephew used to love this nursery rhyme on YouTube called Where is 4. So whenever I say Where is 4, I remember that. Okay. Once again, moving on, I've gone through a whole video on how to name oxyanions. Remember, oxyanions are polyatomic. Poly meaning many, polyatomic. They're made up of many polyatoms, of which one of them is oxygen, right? Ergo, oxyanion. Most polyatomic ions are oxyanions, anions containing oxygen and another metal. Notice notice that when a series of oxyanions contains different number of oxygen atoms, the oxyanions are named according to the number of oxygen atoms in the ion, okay? If there are 2 ions in the same series, one with more oxygen ends with 8, the one with less oxygen ends with I. So in this case here, NO3 minus NO2 minus nitrate. So the template of nomenclature for the anions here is STEM 8, STEM 8. So all 8s don't mean 3 oxygens. No. 8 just means more oxygens. I means less oxygens. Do 8 mean one more than I? Not necessarily. The 8 just means more, I means less. And then same thing here. So the STEM here corresponds with the element that's being used. Nitrogen has the STEM word that's nitra. Went over that in the previous video. Okay, over here, sulfate. Sulf is the stem word for sulfur. H just means more oxygen. I just means still hungry. No, not really. I means less oxygen. Remember, H and I are relative terms indicating more oxygen, less oxygen. No, I just said eight. So yeah. So my jokes are corny, excuse me. Okay, so here we have a series of oxy and ions where you have, I like to start in the middle because it corresponds more with what we just covered, right? If you start in the middle. So a chlorine stem word is chlor. Okay, so you see that throughout. Bromine stem word is brom, like brom. Okay, like bromine. Yeah. Okay, so for chlorine, when you have less oxygens, relatively one less oxygen is going to be I. One more oxygen is going to be A. So you have stem I, stem A to indicate the relative amount of oxygens. But what if it's less than the I? The prefix hypo indicates less than less, because I indicates less already. So then hypo indicates less of a less, which is lesser, right? So hypo is even less. I is already less. So two lesses are less than the I by itself. Anyway, then the eight. Yeah. Just a play on words there. And then eight indicates more, right? I indicates less here. And then eight indicates more, but so does her. Oh. Eight indicates more. So it's going to be more, not mates, more. And then per also indicates more. So we have more. So when you have chlorate, perchlorate indicates more than just the chlorate, okay? The same pattern is observed here. Now, this can work for the chlor group. You can also make this work for the I group. IO minus, IO2 minus. Let me work on that one instead of doing the bromine. Y'all can see the words here. IO4 minus. So the I group, can I squeeze this somewhere? Let me put it on the bottom because I don't have room here. Let me do IO minus, IO2 minus, IO3 minus, IO4 minus, IO4 minus. So do the same thing here. Has a stem word iod. So this would be iodite, right? But it's lower than the regular iodite. So the regular IO2 minus is iodide. The top one will have to be hypo, because hypo is a prefix that indicates less than, right? Above or below the iodide is going to be iodate, right? Because it's more oxygen than the ite. And then more than 8 would be per iodate. Okay, so you have the bromate series right here: chlorates, bromates, iodates. Moving on. Okay, when you're dealing with polyatomic ions, it could be the first or the last one. It could be the first one that's in polyatomic because they're ions because they have a charge. Poly because they're made up of many elements. Polyatomic, so many elements. Ions, that's the example right here. Let's combine that with NO3 minus. Also polyatomic ions here, many with a charge, right? The formula we end up with is NH4NO3. And this compound is called, since the first one is NH4, essentially the ion, NO3, this would be ammonium, right, on your common ion. Nitrate. It also has two names because it's technically type 1 or ionic A compound. Okay, type 1 or ionic A compound. Okay, these right here are common polyatomic ions. Some of them should look familiar to you. You went through it in your common ion test. I'm trying to pick out ones that I don't remember being in your common ion list, but just be aware of it. I'm trying to look at the ones that are similar. There's only one version of acetate right here, carbonate one version. This one here is actually, well, I said carbonate has one version, right? What I meant by was there was no CO3 3 minus. There's no such thing. But if you add a hydrogen to the carbonate, it becomes hydrogen carbonate, right? And then the charge is one less because the hydrogen is technically H plus. If you add the H plus to a carbonate, it becomes hydrogen carbonate, reducing the negative by one and then adding an H to it. Or in the streets is also called bicarbonate, like sodium bicarbonate baking soda. That's sodium bicarbonate, very common household products. It's a deodorizer. I've seen it on many YouTube reels, you know, where it's used to clean grease on a old cooking pan. I mean, they say so, y'all. I've tried it. It didn't really do much. Maybe I'm not doing the chemistry right, but maybe I wasn't patient because they do tell you to put it. They tell you to put the baking soda and then the vinegar on a paper towel and then soak it, and then make sure you put it on the pan for a while. I've waited and I've waited and I got impatient and I cleaned it up and it wasn't really that clean. But they have shown supposedly on those reels, apparently it works. They say. So you want to go through these. Most of these you're done. You do not do peroxide, but you want to be aware of peroxide, right? There's more oxygen than what we're used to, so more per. You have the sulfate bisulfate, sulfite bisulfite. You all see that? We've gone through most of these, so I won't review the list. Okay, so here you're told identify the polyatomic ion and its charge in each compound. Once again, for each of these, do a reverse crisscross, right? So KNO2. My students on campus normally ask me, well, how do you know what are grouped together? For most of these, the easiest one to try to find is a common metal. Try to find the metal by itself and isolate it because metals usually combine by themselves. They're not like in metal and something else, right? Metals are not normally polyatomic metals. So I identify K here by itself. K normally has a charge of plus. That means NO2 has to be minus. Identify the polyatomic ion and its charge. This is it right here. That's its charge. Okay. Next one. CaSO4. Where is the metal? That's common right here. This is the breakoff point. Calcium is normally +2. So it makes the whole SO4 2 minus to make the compound neutral, right? This once again is a polyatomic ion right here. Next one, Mg parentheses NO3 2. What is our metal? Magnesium, very common, charge 2 plus. What's the rest of this? Well, we have 2 nitrates, right? Each nitrate is going to be minus. So there's 2 of them like that. And together they give us -2, which then neutralizes magnesium +2, right? But each nitrate is negative. From the common ion exam, right? Okay, here, name the compound. Once again, when it's an ionic compound, your go-to is to identify the metal. Then you want to isolate that from the rest of the compound. The metal is here, right? So the question is, what's the charge in the metal? Reverse crisscross. If the metal part is separate from the rest of the molecule of the compound, then the number in front of the metal goes back to the non-metal. The number in front of the non-metal, there's nothing written here, goes back to the metal. Since nothing was written here, we imply it was 1. Li plus, the 1 is implied. You don't really write it out. But then Cr2O7, the 2 that was on here comes back up here as negative. So this is dichromate. And this right here is lithium. So lithium dichromate. Don't write lithium ion, right? It's lithium dichromate. Okay, and so we have the lithium dichromate. For this next one here, name the compound. I don't want this in the way, so let's move this here. Awesome. Okay. So now we're trying to name SnClO3, and then this is 2. So once again, separate the metal from the rest of the compound, right? I hope you can see the metal is separate from the rest, ClO3, 2. We need a charge in the metal. The 2 that's here goes back to the metal and it becomes positive. So we have Sn2 plus. The 1 that's indicated here but not spelled out goes back to the chlorates. I mean the ClO3, and this is going to be negative because the negative one is the second one, right? In ionic compounds, the cation, the positive one is first, negative ion is second. Okay, how do we name Sn2 plus? Sn2 plus is 10 2. This is why you want to memorize that list, right? And ClO3 minus is going to be chlorate. Okay, so tin 2 chlorate. Next one, write the formula for cobalt 2 phosphate. So cobalt, cobalt, don't skip the C. Cobalt 2, that's CO2 plus. Phosphate, you memorize this, right? PO4 3 minus. So you have to make a compound from these two. So CO2 plus, PO4 3 minus. Crisscross this. Drop the 3 down here, lose the charge. Put the 2 down there, lose the charge. So we end up with CO3, open parentheses, capital P, capital O, 4 on the bottom, close parentheses, 2. Yep. And this is cobalt 2. So cobalt 2 phosphate. Yep. Oh yeah, that takes care of these. We're making progress. We're moving along. And then the next part I want to talk about. So I'm going to be stopping at the part that has to do with atomic mass, right? Okay. Hydrated ionic compounds. Most compounds, when you get them, they're usually in hydrated form. Not all. If you specifically want the anhydrous, you have to specify. When I started working at Dallas College, I don't want to pause. I want to scoot this out of the way. When I started working at Dallas College, I had to order some copper sulfate. And I was on the website and they were asking, well, do you want copper sulfate hydrated or anhydrous? And I was like, oh, I forgot. That's important. So let me see if I can find you guys a picture of hydrated so you can see the difference between hydrated salts. Give me just a moment. I want to see if I can get a picture between the hydrated salts and the unhydrated so you can see the difference. Okay, let's move over here. So you can see right here, right? This is copper sulfate, usually pentahydrate with 5 water molecules. And this is the anhydrous with no water. On the left, we have the copper sulfate pentahydrate. So pentahydrate means 5 waters. So in the structure of copper sulfate, there are 5 molecules of water incorporated to create that crystalline appearance. And it looks like a jewel. It's not. Don't try to make it into a jewelry because as soon as it gets wet, you sweat, it will dissolve completely to form an aqueous solution. Don't do that to yourself. Then the same compound, after you heat it bone dry, I don't know why they call it bone dry, but after you heat it bone dry, it looks like a powder. The crystalline texture is more crystalline, like a crystal, like salt. Then the dry powder is pretty much dry powder with no water in it, called anhydrous. I'm trying to see other pictures of this. And the internet has a lot of random things that we don't need. Oh, same thing. On campus, we work on this, right? If you have a cobalt 2 chloride hexahydrate, that's what it looks like magenta, purplish crystals, mauve, burgundy crystals. When you heat it up to dryness, when it's till it's bone dry, you have a blue powder. The texture completely changes, right? So we're given different examples here. Copper pentahydrate with 5 waters, magnesium heptahydrate with 6 waters. Each magnesium formula incorporates in its structure 7 waters. 7, man. 1, 2, 3, 4, 5, 6. It was like, it's not enough. 7, I'm good. And then copper sulfate, 5 waters, right? So here we're actually seeing what the structure somewhat looks like, right? So you have the copper and the sulfate incorporating the water molecules around it. And then here, I don't see what we're looking at here. This is a hydrated salt, right? The idea here is informing the salt. The salts are formed slowly. In the process, they absorb moisture from the environment, and that moisture is then incorporated into their structure, the molecular structure, or the formula structure as water molecules, okay? Okay, so how do we name these hydrated ionic compounds? Remember, not all ionic compounds are hydrated. Some of them are hydrated. And the hydrated ionic compounds tend to be heavier. So you have to add the water mass to the molecular mass, okay? So let's go back to this here. Hydrates ionic compounds containing a specific number of water molecules associated with each, like one formula unit. For example, for the formula of Epsom salts, you essentially have magnesium sulfate, like each one compound of magnesium sulfate is attached to, there should be a period here, 7 water molecules. Okay, we don't see how it's connected, but it is connected. So to name it, you have to call it, the systematic name is magnesium sulfate for the ionic part. Hepta. Hepta is a prefix describing the number of water molecules. Hydrate. Okay. Another example is cobalt 2 chloride. You will name the ionic compound part like an ionic compound, like any regular ionic compound, right? And then for the water part, you have to say how many water molecules are attached, right? There should be a period here. So it's not carbon, sorry, cobalt 2 chloride, that's it, with 6 waters, so hexahydrate. Remember, when you're figuring out the mass, you have to add in the water mass. So these are the prefixes used to describe the hydrated compound, okay? So we have hemi, mono. Hemi stands for half, mono, ditride, tetra, penta, hexa, hepta, octa. You also have nona, that's 9. And you have deca, that's going to be 10, okay? So this example here is calcium sulfate, right? Just calcium sulfate, hemihydrate, barium chloride, hexahydrate, because there's 6 of them. And then copper 2 sulfate, because that's an ionic B compound. Pentahydrate, right? Copper, it should be copper 2 sulfate. I feel like some symbols are missing here. Pentahydrate. That's what it should be. Okay. Okay, remember when it comes to the mass, you have to add the mass of water. If it's 5 waters, you add it time. Each water is equal to 18 grams. So if it is 5 waters, you do 18 times 5. Okay. Okay, going back to this right here. Here's the big question, the $1 million question, maybe the $5 question. In this inflationary market right here, it'd be like the $1 billion question, right? Anyway, how do you have half a water? So we're saying we're given the amount of water per one formula of ionic compound. How do you have, if this is a water, how do you have half water? Like, do we have half H, the top part of the H, and then the top part of the 2, and then the top part of the O? Like, how does that work? Remember, Dalton said that the atoms combine in wholes to form a compound. Elements combine as whole elements, whole atoms to form compounds. So you can't have a half atom. So how can we have half water on calcium sulfate? Okay, give you a moment to think about that. Okay, and try not to make the video too long. What they're representing here is the amount of water molecules per 1 unit of the formula, right? What is constant here in the amount is the amount of the ionic compound. It has to be 1 each time. That just means to get half water, the 1 water is tied to 2 calcium sulfates. Yeah. So per calcium sulfate, you're equally breaking this apart, or you're equally splitting the water to give half to one calcium sulfate, the other half to the other calcium sulfate. Okay. So if you're figuring out the mass of calcium sulfate, you figure out the mass of calcium sulfate, right? And then add half water, that would be half of 18. So that would be what, 9? Yeah, to the mass of calcium sulfate. In covalent bonds, remember, we're kind of looking at this from the point of view of Lewis. So to form a bond, we have to have shared electrons. Covalent bonds, to form a bond here, you're sharing electrons. But how do you know how many to share? We're told here, electrons that are shared by atoms are called bonding pairs. Electrons that are not shared by atoms but belong to the particular atoms are called lone pairs. So once the sharing is done, then some electrons belong to both elements, some belong to just one. So let me try to show you how this works out, right? First of all, let's start with the Lewis bonding. Because I feel like, yeah, let's just do it while we're here. In the Lewis bonding, the beginning starts with the Lewis symbol. So hydrogen is in group 1. In group 1, it has 1 dot, right? Oxygen is in group 6. Group 6, it has 6 dots. So let me try to move this out of the way so I can draw my 6 dots. Group 6. 1, 2, 3, 4, 5, 6. Okay. When you're trying to pair electrons, valence electrons, and mind you, when Lewis is drawing the symbols, the dots represent dots equal valence electrons. Okay, that's the bottom line. So hydrogen has 1 valence electron, oxygen has 6 valence electrons. What you're going to do is pair unpaired electrons. So you have to pair unpaired electrons, right? You look over here and you see that the hydrogen compare, the electron of the hydrogen compare with that oxygen electron, right? And then over here, you can bring in another hydrogen with this electron to pair with this right here, okay? So to kind of help you guys some more, can I change the color here? Maybe I just add a highlight. Where's the highlighter? Let me add the highlighter here and the highlighter here for you to see the difference. So in the end, the hydrogen that's glowing green and it's 1 green electron right here is being shared with the oxygen. So you see the ones that have different colors, let's use the red here to indicate the electron from the hydrogen. The mixed color, red and black, that indicates shared electron. Shared electrons are bonds, right? So shared electrons that are shared between elements are equal to bonds. And then lone pair electrons belong to the one element by itself. So these are not shared, or let's call them unshared electrons. Okay, in the arrangement, they share electrons so that they can both have filled orbitals, right? Now, oxygen ends up surrounded by 8 electrons. So oxygen ends up having an octet of electrons because it has 8 electrons surrounding it. But hydrogen only has a duet. Duet stands for 2 electrons. Oxygen was surrounded by 6 electrons, right? 1, 2, 3, 4, 5, 6. By pairing with hydrogen, I'm going to use a different color now. Let me use green. The hydrogen brings its own electron here. And you can see where we have 2 different colors. These are the shared, right? For shared electrons, each element in that's sharing the electrons has equal access, full custody, okay? They have equal access to the shared electrons. So shared electrons means elements have equal access. It's like, yeah, shared custody, equal access. To explain this, I kind of look at it like you're married to somebody and you'll have a shared account, both your name is on it, then that will be like this one here, right? So elements have equal access. The people with the names on the account, they have equal access. Either one can go to the bank and do something, right, with that money because both their names is on it. But let's say that happens. So oxygen has a shared account with hydrogen. So both have access to the electrons in the account. These are the 2 electrons in the one account, 2 electrons in the other account. So in this relationship, hydrogen and oxygen have a shared account. If you look at it, hydrogen doesn't have any other account besides a shared account. On the other hand, oxygen has some electrons stashed away, some cash in some 2 accounts. We don't know what the accounts are, but who doesn't have access to them? Hydrogen, okay? So where these 2 electrons are, they're called lone pairs because guess whose name is on it? Only oxygen. So this is like, oxygen is like, just in case. I'm going to have this account on the side. I probably should have hydrogen's name on it, but I don't want to have hydrogen's name on it. This is going to be my backup plan, right? Too much, I know. This is oxygen's lone pair account where only oxygen has access to them. Yes, elements do that too, okay? But you want to recognize lone pair electrons versus shared electrons. Shared electrons, these translate into bonds, right? Because they're co-owned, they're equally owned. These are bonds. They're equally owned by the elements that have access to them, so they're called bonds. Okay, remember, from what we're seeing here, bonding pair of electrons, each bond is 2 electrons. Each lone pair also 2 electrons. So there's a theme here of 2 electrons, right? And then you can look right here for the oxygen surrounded by 8 electrons, hydrogen surrounded by 2 electrons, oxygen obeys the octet rule, the hydrogen obeys the duet rule, and that's pretty much it, okay? So single covalent bonds, when two atoms share one pair of electrons, it is called a single covalent bond. And they can share many, like we're seeing, I already told you about the octet and the duet, so I'm going to skip over that part. They can share many, like what's going on here. To form that structure, you're going to look at the Lewis symbol for each oxygen, also in group 6. Remember, each oxygen is in group 6. You want to have your periodic table nearby. Draw your dots, 1, 2, 3, 4, 5, 6. You can see we have 2 unpaired electrons here, right? Let me move the oxygen lower so we can see how this works out. 1, 2, 3, 4, 5, 6. Now you want to share the unpaired electrons. So share these 2 electrons here, share those 2 electrons there. And so this translates into the shared electrons. I'm going to draw them as dashes. And the lone pair electrons will be pairs as dots. So you see here with Lewis's symbol, Lewis likes to use his dots, right? So technically the shared electrons are here. Let me use a different color to indicate that. The one on the right will be the green. Oh, let me use a different color. I forgot that some of you may not be able to see that very well. Let me use purple, bright purple, 2, 3, 4. Okay. These are the oxygen on the right will be the bright purple one. The one on the left will be the bright red one. Oops, that's not red. 1, 2, 3, 4, 5, 6. That's the oxygen on the left. Where we have 2 colors, that's the bonding electrons. These are co-owned by either oxygen. Okay. So these are shared electron pairs equal bonds. Okay. And then here we have lone pairs. Lone pairs, I've already told you the story, the backstory on lone pairs belongs to the element that is attached to. So the elements that can have double bonds with each other or multiple bonds with each other are carbon, nitrogen, oxygen, sulfur, phosphorus. Okay. Okay, some elements can triple bond. Oh, by the way, remember when we're bonding, we're sharing the unpaired electrons. So don't forget, when you're bonding, you want to share unpaired electrons. Okay. So where am I doing? How am I doing? Okay, 46. I'm trying to make sure that all the elements are working here. That I'm sharing my screen and I'm recording, right? Because a lot of things can happen. Okay, moving on here. Our next one is showing how we get triple bonds here. If you draw the element symbol for nitrogen, each nitrogen has got 5 electrons. So we got 1, 2, 3, 4, 5. That's 1. For our next one, let's do purple one. 1, 2, 3, 4, 5. So we're sharing the unpaired electrons, right? So again, you're going to share these unpaired electrons, share these unpaired electrons, share these unpaired electrons. So in the end, we end up with 3 lines symbolizing the sharing, and then 2 electrons on either side, right? The lone pair here for the left one, lone pair for the right one, and they're sharing 6 electrons, okay? So here we have a triple bond. Remember, each one bond represents 2 electrons. Elements that can triple bond with themselves is carbon, nitrogen, oxygen, and sulfur. Okay. Our final part before we go to the other video that has already been recorded is naming molecular compounds and even recognizing it. For molecular compounds, we're told the formula for the molecular compound cannot readily be determined from its constituent elements because the same combination of elements may form different molecular compounds. For example, this is showing you nitrogen and oxygen. Oh, when we did multiple proportions, we did something like this, right? the same elements can combine to form many different compounds. So N and O can form NO, as in no, NO2, N2O, N2O3, N2O4, N2O5. These are all the combinations that can form between nitrogen and oxygen, right? So this is very unique. When we're naming these compounds, we have to follow a template. But besides that, do not simplify these ones. Do not simplify. No. Molecular compounds are left as is. Do not divide this by 2, divide by 2 to get NO2. No way. That's a completely, this formula here, completely different from that formula there. Completely different. When it comes to identifying molecular compounds, like I showed you in the video, there are 4 components to the name, right? You have a prefix, the element, prefix, and then the anion. The anions here tend to be monatomic ions. I haven't necessarily seen polyatomic ions. So that's good news, right? That most of these are binary. So they're binary molecular compounds. Okay, so it's 4 parts to the name. Prefix. I want to add my own spin to it. Then the element name is the first one. Remember, in this one here, all the parts are non-metal. So prefix, element, non-metal. Prefix, again. And then the element this time will be named as an anion. So like stemide or whatever. Okay. So what prefixes do we use here, you ask? There's no hemi here. We start with monos because the atoms are combining as whole. So mono, no fractions here. 1, 2, 3, 4, 5. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay. But when it comes to naming the first one, you can use any of the prefixes except for mono. So I usually write here, no mono. You can't use mono for the first one. Probably going, what? You already know this, right? The gas I'm currently exhaling as I'm talking to you is carbon dioxide. The formula for carbon dioxide is CO2. There's only one carbon. Oh, by the way, the prefix here stands for number of atoms, right? Number of atoms. So the one on the left would be number of atoms in the first element, number of atoms in the second element, right? If you look at this right here, how many carbons do we have here? Technically 1. So the name should be monocarbon dioxide because we have 1 carbon, 2 oxygens, but we don't call it that. Not even in the street, we just call it carbon dioxide. So we're all familiar with this nomenclature system. We're not really familiar. We've been using it though, right? So all the prefixes are possible here to describe the number of atoms in the element, except for mono. So no mono. This one here is a free for all. Use them all. Use. That's not how you spell use, right? I'm close to the end. My brain is already shutting down. Use whichever prefix you want, as long as it accurately describes the number of elements in the second one. First one is written as an element, second one is an anion. So let me write this down finally so I can wrap this up. Because I've already done the video, right? Explaining this in the other video. So yes. So we have prefix here, no mono, element, prefix again, stemide. Okay. And the stemide is the name of the anion. So let's go ahead and see what we have here. Oh, great. So close to the end. Let's go ahead and name this. While we're here, I'm going to write this down. How many nitrogens do I have in this formula? The one is implied, right? So don't use mono. I'll just write it here, but I'm going to cross it out. So mono nitrogen, because there's 1 nitrogen as an element, not nitride, right? Triiodide. Triiodide. Cross out the mono, so nitrogen triiodide. That'll be your final answer for the first one, nitrogen triiodide. Yep. We have this here. So what I want to try here is, let me do PO5 for this one here. For B, let me do P. Actually, let me do P2 instead of just P. P2O5. So this would be di because it's 2. Phosphorus. 2 phosphoruses. And then 5 pentaoxide. Okay. I did this to show you that this is because you have an A and O here. The convention is to drop the A so it becomes pentoxide. So diphosphorus pentoxide. Okay. And that will be this one here. Next one is P4S10. Tetra for 4. This is a lot of phosphoruses. You know what? Let's not do that one because this is already done down here. I'll just show you that one. Let's do Cl2O7. Dichlorine, right? I don't say chlorine, chloro. 2 chlorines. Hepta 7. Hept. But it's oxygen, so heptoxide, not heptaoxide. Yeah. 2 chlorines, 7 oxygens. So dichlorine heptoxide. Yep. Okay, for the one I skipped over here, we did nitrogen triiodide. The 2 I's stay. I don't know what they were thinking. I feel like it was Friday. They were over it. And then this one here, phosphorus pentachloride. That one is fine. The mono is dropped. Here we have tetra for 4 phosphoruses, right? Decasulfide. So AS is fine. AC is fine. II is fine. The other elements, say you have SO3 as a molecule. You will name this sulfur, right? Trioxide. So this would be 1 sulfur, the mono is implied, 3 oxygens. It would be trioxide, not troxide. Don't ask me, y'all. I wasn't invited to that party. I wasn't even born. Anyway, that's the rules for this. So we have ended right here. The next video will start over here and y'all will see it. Actually, that video is already posted, right? This was the in-between video that was missing. So hopefully I've done it right this time. Okay, see you guys next time.